Okay, we're going to make some magic here. We're going to discuss continuity of a function with the epsilon delta definition. Okay, so, excuse me, this is the same definition basically that we use for a limit, right? Which we discussed before. The only difference is really with continuity, it just says that as the limit approaches c of f of x, that equals f of c. Okay, so remember with the limit definition stuff, we have to show that we had f of x minus L was less than epsilon when x minus c was less than delta, right? Okay, so let's just consider a function here. We'll give you a nice good example. So let's just say we have this linear function 2x plus 1. Okay. The claim we want is that the absolute value of f of x minus f of c, okay, of course, is going to be less than epsilon. Okay. Now, this f of x minus f of c is just nothing more than what? 2x plus 1 minus, that's supposed to be a parentheses, 2c plus 1, because that's what f of c is, right? And we'd like that to be less than epsilon. I can't draw an epsilon. There we go. Well, this simplifies the 2 times x minus c. So we could divide both sides by 2 and get x minus c, absolute value of that, less than epsilon over 2. So then the delta that we want then will be delta equals epsilon over 2. Now what this means is that when you look at the graph of this thing, okay, it's going to look like this. And let's say we pick, whatever point we have here, c, okay, and this over here is f of c. Now that means whatever epsilon you pick, okay, perhaps you want epsilon and you just pick epsilon to be a half. Okay, so this would be f of c plus 1/2. Okay? And down here somewhere would be f of c minus a half. Now if you look at that little interval that's created, and you look at those y-coordinates, it's going to surround c. And what that means is the delta that I need would be half of that, because delta is epsilon divided by 2. So as long as we stay within 1/4 of that x-coordinate, the y-coordinates will be within 1/2 of each other. Sorry, my allergies are getting me. All right. And you can, and that works for any value for epsilon that you pick. Okay. So what we want to do then is, this is what we've done is just kind of backwards of what we need to do, but it's the easiest way to find the delta. So to show something is continuous, we start at the back end and say, okay, well, let epsilon be greater than 0 be given, and delta equaling epsilon over 2. Okay, so all that means is that you can pick any epsilon that you want, and once you pick that, then we have a value for delta as well. Then we start off and say, okay, well, let x minus c be less than delta. So we're going to pick something really close around the x-coordinate. Well, because we know what delta equals in terms of epsilon, we can just switch that and say, okay, well, that's epsilon over 2. We can multiply 2 by both sides. That's less than epsilon. Okay, we can pull that 2 inside and distribute it. Now I'm going to add 0. So we're going to add 1, and then we're going to turn around and subtract 1. So in this case, we do have exactly what we need. F of x minus f of c is, in fact, less than epsilon whenever x minus c is less than delta. So therefore, f of x is continuous. So notice before with the limits, the value of the function didn't have to equal the limit. But for continuity, it does. Now what this means is that basically you can draw the graph without picking up your pencil. Okay? There's no breaks in the graph or anything like that. Now you might come across things that do. When that's not the case, there are different types of discontinuities. Okay? So we might have something like a function that looks like this. There's just a hole in the graph. Okay? Something that happens like this would be what we call a removable discontinuity. Okay? Now, it's removable because there's just a hole in the graph. Think of it this way. You could plug that hole like that. An example of where this might happen might be at, let's just say, if f of x equals x squared plus 1 over x minus 1. Right? Now, the limit as x approaches 1 for this graph, okay, for this function, would be, let's see, that's going to be 2. Okay. Well, we could define this as a piecewise function. Now, this is not a continuous function because we have this discontinuity in the denominator. If we plug 1 in and we try to evaluate f of 1, that's undefined because you can't divide by 0, right? But if we had, let's say, a new function, and we said that was x squared plus 1 over x minus 1 when x is not equal to 1, and it's equal to 2 when x does equal 1. We make a piecewise function. Okay? We would get this straight line from the top function, and then when x equals 1, we define it at 2. That plugs the hole, and now I could draw that graph without lifting my pencil. So that's a removable discontinuity. It's like a hole in the graph that you can fill. On the other hand, maybe you simply have f of x equals 1 over x. When you go to draw that graph, okay, you're going to get something like so. Okay? So now there's a discontinuity at what x equals 0. But there's nowhere to plug that because it's not just a simple hole in this case. I could try to put something up here, but this is just going to go past it. Darn it. Okay? But you can see easily there's nowhere to stick one single point that would join those two pieces of the graph together. Okay? So that is definitely not a removable discontinuity. Okay? So the removable ones, you got to be able to plug the hole. Okay? So whatever the limit is, the other piece of the function has to be able to be equal to that limit. So a limit has to exist, and it's the same from both sides. Okay? And then you can just define the function to equal that point. Now, the function would have to be undefined there, right? If I already had a function, let's go back to this one. If I already had a function and it had a hole in this piece of it, okay, so a little hole there, and then our function was defined up here, we couldn't add another point right here, okay? Because then it wouldn't be a function anymore. We would have to remove one point and then add in another point. And that's giving us a different function, right? So we can't remove stuff in order to plug the hole. The hole just has to be there. Um, so you want to be careful about the removal of discontinuities. Right? All right, so hopefully this will help a little bit. Now, just as real quick, the intermediate value theorem, which you'll see. Okay, now that's important. The intermediate value theorem, kind of in layman's terms. Okay, so intermediate value theorem. I'm going to abbreviate it. Starts off and it says you have to have a continuous function on some interval. Okay, so we got some interval a and b. Okay, so f of x is continuous on the interval ab. So I can draw the graph without picking up my pencil. Okay. Then if you have some function in here, whatever. Okay. This is the point then be f of b. And here we'd have the point, a f of a. Okay. You know what? I'm going to make it a little bit more dramatic. So let me try to erase this. And it's not going to erase. So you know what? Heck with it. So that's the point B, f of B, and down here is the point A, and then whatever its y coordinate is. So the intermediate value theorem just simply says that if it's continuous, then that function takes on every single value in between those. Okay? That's it. That's all the intermediate values. As long as it's continuous on an interval, then the y-coordinates, there will be a y-coordinate on that graph for every possibility in between f of a and f of b. Right? Now, so that means, though, that somewhere in between there, we have a value of the function, a value for the x-coordinate c that's in there somewhere. So that way, if you pick any y-coordinate, f of c equals L, that you're guaranteed to have one in there. Okay. Now, we use this intermediate value theorem actually quite a bit, especially like when finding zeros. Okay? Let's say we have some crazy little polynomial. Okay? Get another page here. And let's say that f of x is equal to x cubed plus 1. Okay, that's not real crazy, but it'll demonstrate what I want it to. Okay. Now, if we want to find the zeros or the x-intercepts of that function, one of the ways that we can do that is just start narrowing it down. Okay. Now, I know that if x is a negative 2, then that means f of x, or f of negative 2, right, is going to be equal to negative 7. So I have this y-coordinate down here at negative 7, okay, when x is equal to negative 2. So let's just say it's right here. Okay. Now, I also know that if x equals 1, then f of 1 is going to equal 2. So when x equals 1, it's above the x-axis. It's up here somewhere. Now, by the intermediate value theorem, it went from a negative to a positive. So I know somewhere in between, it has to cross that x-axis. Okay, because 0, okay, is between negative 7, all right, and 1. Or 2, rather, sorry. Okay. So x-intercept exists somewhere in that interval. Okay. Now, I can narrow that down further and say, you know what? Let's say instead of 1 or -2, it looks like, it's much closer to the other side, so I could just go, you know what happens when x is -1.1? Now, if x is -1.1, grab my calculator for that one. Why did I say 1 point? I said -1.1. Then f of -1.1 is -2.3. So I've got it narrowed down, okay? Because we still go from negative to positive, right? So somewhere between -2.3 and 1, we have an x-intercept. And I could continue further narrowing this down by choosing that interval to be smaller and smaller and get any degree of accuracy that I want. Okay, and it's guaranteed that somewhere in there is that x-intercept. So we could estimate it really, really closely just using this intermediate value theorem. That's really all it's saying. The intermediate value theorem just says that for a continuous function, when you look at the y-coordinates on some particular interval, it takes up all of them.